All right, I don't know why this is not going to let me into my files. I'm trying to get there. There we go. Approximation.
Stop. Yes, Tyler. Oh my gosh.
All right, guys, jumping back to where we were yesterday, we did not get where I wanted to be. So I want to quickly run through these formulas. I need y'all's attention. I want to quickly run through these four kinds. I don't even think we got to trapezoidal, and we kind of rushed through midpoint. But I want to quickly go over all these four and then show you some examples and practice them. I'm not opposed to adding an extra day in here if we need it, but just looking through what we're doing, I think we're going to be fine. Kind of catching up today. But again, finding area between a curve. And by the way, most people say area under the curve. Like if you got a calculus, they're like, oh yeah, the integral calculates the area under the curve. Well, the area under the curve goes forever, right? The x, y, and axis keeps going down forever. So make sure you understand it's the area between the curve and the x-axis. And then on Monday or Tuesday, we'll start talking about accumulation. What does that mean when the curve is above? What does it mean when the curve is below the x-axis? Or sometimes we accumulate to the right, sometimes we accumulate to the left. So those things will affect the accumulation process. But for now, we're going to do these just thinking about Riemann sums. We're going to calculate areas. This is going to be curves above. So most real life examples, we're dealing with positive situations. Okay, we don't go, or whatever, speed, whatever, acceleration, most of them, a lot of them are positive. So those would be curves that are above the x-axis. But for now, just work with me. So this was an example of a right hand. I was showing you right hand Riemann approximations. And right hand means once you decide where your base is, you bring up that rectangle until the right side hits the curve. The left side may be above the curve, it may be below the curve. It depends on what the curve's doing. But you have to read and see, is it a right-handed accumulation? Is it a left-handed? I mean, a right-handed Riemann sum or a left-handed Riemann sum? And it possibly could be a midpoint Riemann sum, which means when you find the base, instead of plugging the right side into the function to find the height, or the left side to find the height, you find the average of those x's, find the middle of the base, basically, and plug that in to find the height. But the bottom line is you have to remember on all of these, you're finding areas of these individual rectangles or trapezoids. So if you think about going back to this, and I'll come back and do those. If you think about these examples right here, on a right rectangle, you need to know where you begin and where you end. So if I was going from 2 to 10, x equals 2 to x equals 10, and sometimes it's time, like I'll go, how much blah, blah, blah did you accumulate or did you get from time 2 to time 8 or time 2 to time 10? Whatever it is, find the time that expired, 10 minus 2, which is a total of 8. And then depending on how many rectangles you have, divide it by that number of rectangles. And again, we haven't seen this example yet, but sometimes I will tell you the bases. Sometimes they'll say, hey, the first interval has a base of 1. The next one has a base of 3. Next one has a base of 2. Next one has a base of 5. If I tell you that, great. You know those bases. If I don't, you have to figure out how to divide the total by the number of rectangles. And it's always end minus beginning for the total. In this case, divided by, this would be 8. If I divide that by 4, I get a little base of 2. And you can see 2 to 4 is 2. 4 to 6 is 2. 6 to 8 is 2. 8 to 10 is 2. If I go from 2 to 10, a total of 8, and then divide it by 4 again, 2, 2, 2, 2. And if I divide it by 8, then your bases would have 1, 1, 1, 1, 1, 1. If I divided it by 16, your bases would all be a half. Half, 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 half. And for each of those bases, you have to know, like if it's a left one, you go, okay, if my base begins at 2, I'm going to plug 2 in to find that height. And if I move over, like in this case, I moved over 2, well, I would plug 4 in to find, this is a right rectangle. I would plug in 4 to find that height, 6, 8, 10. And those individual heights I would pair with the bases to find areas. But on a left rectangle, I need to know the left sides, like 2, 4, 6, 8. You won't even use the 10. It looks up to find the total. And you plug in 2, 4, 6, 8 into your function, whatever it is, to find the height. Are y'all seeing this? But on the midpoint, which we kind of were talking about right at the end, if those were your bases from 2 to 4, 4 to 6, 6 to 8, 8 to 10, you have to find the middle of 2 and 4. So average them. And I know between 2 and 4 is 3. That's pretty easy. But it might not be so easy. It might be between 1.7 and 6.5, right? So just average those to find the middle and plug that in. So when you plug in whatever that middle number is, you're basically plugging it into your function to find that height. And you're using that height and that base to find this area. And midpoint's probably going to be more accurate. Because if you think about midpoints, there's always a little over approximation and a little under approximation. And the idea, not always, but typically, it wouldn't be that way if it was straight like this. But typically, you've got a little too much and a little too little. A little too little and a little too much. A little too little and a little too much. And the idea is that they kind of cancel themselves out. Does that make sense? So this is going to give me a much better looking approximation, kind of overestimating and underestimating, over and under, than something like maybe this that has a little bit of over, but tons of under approximating, right? Or this one that has tons of over and just a little under. So the idea is a midpoint's a little better, but ironically, they don't use midpoints very much. They love to use midpoints with tables, and I'll talk about that in a second. And what I mean by tables is a table of values would give you all the x values and all the y values, which I think is great because you don't have to find the y value. You'll see that in a second. It's literally right there in the table for you. Now, trapezoids is very common and actually pretty accurate because even though I might be like, in this case, because it was like this, I had a little bit too little, too little, too little, too little. If the curve was doing this, sometimes you got a little too little too much. But the great thing is when you under approximate very little. And when you over approximate very little. Are you with me on that? So trapezoid, if I had one go-to, I'd probably go with trapezoid, especially since I don't have to find that middle number, okay, which makes it a little bit easier. But trapezoid, you got to remember the formula for a trapezoid. So here's how you learned trapezoid, and then here's how we'll do area. When you were in geometry, way back as a freshman or whatever, you learned probably that the area of a trapezoid was, and it was usually based on a picture like this, wasn't it? Something like, you know, that, and you said, well, there's base 1, and then there's base 2, and then there's this height right here, right? And you learned that it was probably 1/2 times the sum of the two bases times the height. And the variables might be switched up as 1/2 h times the sum of the two bases. What is that really saying? Yes, but what is 1/2 B1 plus B2 really saying? The average of the bases. Now, notice that's different than the midpoint, which didn't average the two heights. What did it average? The two x values. So in a midpoint, you average the two x values and then plug it into your function to find the height at the middle. Here, you're kind of averaging these two bases times height. Well, here, I'm kind of looking at this thing like this. So here, I don't call this B1 and B2. I call this height 1 and height 2, and I call that the base. So I'm kind of switching the B's and the H's. Are you following me? So the area of, I'm going to call this area 1. So the area of that first triangle right there, that first trapezoid right there would be 1/2 times H1 plus H2 times base, except most people write it like this. Go. So most people write it like this: 1/2 times base times H1 plus H2. And that's how your notes, I think, write it. And the reason why they write it like that most of the time in textbooks is because most of the time in textbooks, we're dealing with situations where our bases are all the same. So if every area has a 1/2 and every area has a base, what could I do? Factor out the 1/2 and the b, and then all I would have to do is add up all those h's. So that's why they do that. There's even a formula at the bottom of this page where I have it all simplified and condensed. You don't have to memorize it. When I was in calculus, I memorized it because we used it, and we had so many big things where we had maybe 13 trapezoids, and it was very tedious. But nowadays on the AP test, they usually only have like 3 or 4 or 5 trapezoids. To me, it's better. I just memorize the area formula and then just do it 5 times, and I'm better off. And by the way, on the AP test, there are apps for your TI Inspire. There might be some. I'm sure there's some for the 80, the crappy 84.
Oh, Mr. Hurry, I know you did not.
I'm sure there are some for the 84 also, but those apps that you can look them up on and probably download them, but they're Riemann approximation apps, but they don't account for different bases. Okay, so that AP got wise 20 years ago when people had these apps that were doing all their Riemann, they had all the forms. But listen, on the AP test, if you have your calculator, you can type these formulas in there. Nobody's stopping you. Now, if you do that in Ree's class, you're going down. Like, she doesn't want you to do that. But I recognize that half of the AP test, literally half of the points, or almost half the points, come from calculator problems. So I don't mind you having it in there. But keep in mind, we have a 2-day test. And one of those days, you're not going to have a calculator. So if you don't know what to do, and you have no idea on the non-calculator part, you're not going to have those formulas ready for you. So you can memorize it like this, or you can go, and I kind of like this. I did a little survey last year, and last year, most of the people liked that. But I kind of like going average the heights times the base. The average of the heights times the base, because that's what you're doing. You're doing a half of the sum. That's the average times the base. You do what you want to do. I'll recognize it no matter how you have it written. Okay? Now, again, to find these heights, what are you going to need to know? You're going to need to know that x value and plug it in and find f of 2, and that x value 4, plug it in and find f of 4 to find those heights to get them in there along with your base. So those are the 4 Riemann sums that you will be tested on and that you will need to know for the AP test. And again, it's not overly difficult. If anything, it's tedious. But if you're not thinking of what's happening and you're just memorizing, it's going to be harder for you because then it becomes just very formulaic. I would rather understand it and kind of think that way. Now, you do need to know your trapezoid formula. So I want to look at some of these and see if we can do. And these are all the little mini formulas here, if you want to look at them and know them. But let's just look at some of these problems and see what happens. So right here on number 1, it says, for each problem, approximate the area under the function for the specific number of rectangles or trapezoids. You were to do all 4 methods to approximate the areas. So on number 1, for A, we're going to do the area using left, right, midpoint, and trapezoidal approximations, but with 4 rectangles or trapezoid. So let's think. And by the way, you should, at the end of the time or whatever, be able to do this kind of visualizing the graph in your head. But for now, if you can't visualize it, no problem. Just sketch a little something. And you don't have to sketch the graph. I usually put like a little wiggle to represent the graph, and you'll see that in a second. So even though that graph is a parabola, it's opening upward because it's +1, whatever. So here's kind of my thinking for 1A, the area with 4 left-handed rectangles. So I'm kind of thinking to myself right now, all right, if I had some parabola right here, right? And I'm finding the area from -4 to 12. So I'm going to say, all right, let's just pretend the left side was -4 and the right side was 12. Who cares about the y-axis, all right? How much, and I want to find all this area in here under the curve, between the curve and the x-axis. So right here, what is the total span from -4 to 12? And this is me finding the base. So I'm going to go 12 minus the -4. Now, a lot of you can get 16 out of that. Great. Now, I want 4, number of rectangles. I want 4 rectangles. So I divide that by 4, and 16 over 4 is 4. So what that means is the length of each base is 4. Are you with me? So if I'm doing the area here, and by the way, what I'm really doing, in case you haven't put this together yet, I know I wrote area. What I probably should have done is write the integral from -4 to 12 of this function is approximately, and I'm not going to do what Chris knows how to do from Physics C. He knows actually how to integrate that from -4 to 12 using what we call the fundamental theorem of calculus, right? Because you have to know that in physics for probably basic functions. And now that he knows integration, he can probably do it for anything. But we're not going to use that. We're using our approximation. So what do I do for left rectangles? I take the base, which is 4, right? And I multiply it by the height. And I'm going to do that for each of my 4 rectangles. Okay? Now, because this one is left, think of my bases. If I were to break this up into 4 parts, right there, I'm bringing the left side up. So what is the x value of the left side of this rectangle when I bring it up? -4. So I want to plug -4 into my function. That's f of -4. And I want to use that as my height. Because really what I'm doing is I'm bringing this up and I'm going until the left side hits. So I want that height and that base. So I plug -4 into the function and I get 16. Plus 12 is 28. Plus 4 is 32. And that is my height of that little base section right here. And I never had to actually sketch a real curve or visualize it exactly or do anything like that. Does that part make sense that I just did? If it doesn't, I'm going to do it 3 more times. Okay, now, the next, if that's at 4, right here, right? So I already plugged 4 in and found that height, 128, whatever that is. What would be the next x value if the base is 4? 0. And again, I'm using the left side because it's a left rectangle. So now I bring that up and it's the left side. Maybe it looks something like that. But again, now I want this second height, but I got to use 0. Well, 0 is a little easier to plug in, but hold on a second. Hey. Hello. Sure. Hey. Okay, so what do I plug in if I want the left side of the second one? 0. I plug 0 in. So I'm looking for f of 0. So when I plug a 0 in there, I get 4. Great. I have that area, 16. Now, then I got to move over another 4. So since I was at 0, when I move over another 4, I'm now at 4, right? So I got to find f of 4 to find that height. So f of 4, this is probably going to be a little bit of an under approximation if the curve looked that way, but I don't know and I don't care. Math will help me know, right? So I plug 4 in there and I get 16 minus 12, which is 4, plus 4, which is 8. And then finally, I move over another 4 to get to 8. And I plug 8 in there to find that height. Looks like I might come up a little short if the parabola looked like this. Now, it might not look like this. I mean, this parabola could have dipped over here, and it might be moving straight up. I don't know, and I don't care, right? I'm letting the math do the math. But I just drew a little thing right there to kind of, I could put a squiggle. As long as I'm visualizing, I'm really just looking for what the actual x values are. So I'm going to plug in, that was the first one. That was the first, that was the second, that was the third. So finally, I plug in an f of 8. F of 8 in there gives me 64 minus 24 is 40, plus 4 is 44. And at this point, I'm just careful to do the math. So that gives me what? A 128 plus a 16 plus a 32 plus a 176. This right here gives me a 144. That gives me a 208, so 352, if I haven't made a careless error. So what is my area using left rectangles? 352. Now, Sorry?
You said triangles.
I say triangles all the time. I'm sorry. There's nothing to do with triangles. So when you hear that, that just means rectangle or trapezoid. You're welcome to correct me. Feel free. But for some weird reason, I do that all the time. Every year, I cannot get out of it. I'm better than I used to be. One year, at the end of the period, they're like, you said triangle every single time. I was like, no, I didn't. Check the video or whatever. Anyway, now watch what happens. What's different when I use, now notice I never even used the 12, did I? And you're like, how can that be accurate if you never use the 12? It probably isn't. It's an approximation. But if I had more than 4 rectangles and I had 100 rectangles with a base that was like 0.6 would not have much error, would it? And 1,000 rectangles would have even less. And an infinite would have none, because if you have an infinite, your base literally goes to 0. And that's what an integral really is doing. So we will literally use a right-hand rectangle formula to define the integral, because it doesn't matter once the base goes to nothing. It's like sliding in sheets of paper in there as opposed to fat rectangles. So it doesn't matter with the calculus. You could have used any of the formulas. But I would argue if you are going to use just 4 of something or 5 of something, a trapezoidal or a midpoint is probably going to get you better in a more concise, clear way. I used a trapezoidal, and I went back and looked at that piece of sod I have left. I mean, it is literally, I put it in the front because I knew I was going to have to sod the front, and then I broke my hand. I broke my hand in July, right in the middle of a giant yard project. So I couldn't finish doing the front. The front looks terrible. Like there's a giant mound of dirt, like literally this high. It's a big hunk of dirt. My wife is like, ugh. We got some stuff done. I actually hired a little out, but this spring, sod's going down to the front.
Sod's going down?
It's so ridiculous. Back then it was $220 a pallet. It's up to over $300 a pallet now. It's going to cost me probably an extra $800 just because I broke my stinking hand.
Mr. Hurry, let me know when you want some help with sod.
Dude, have you ever laid sod?
Yes.
Have you?
Oh.
Is this an 8 maybe? Okay, I don't, whatever. I may take you up on that, but I don't know.
It's like a buzzing noise.
I once had a couple guys come out there and do that for me, and I made them ribeyes or something like that. And I mean, they were like, dude, that stinks. I mean, laying sod is awful. Because you're like grabbing a big hunk, you're getting over there, even if you have a wheelbarrow, you're jumping in there, you bring it over there, you're getting on your knees. It's no fun.
You ever
You have
like,
an alarm going off on your phone, sir?
It's possible. They go on all day long.
no, like mixed
No?
concrete.
You-
I didn't know, like,
Maybe
Oh,
I'm
my
just
daughter's
doing-
like me.
I'm just-
All right, so right here, guys, let's do a right rectangle. Now, on a right rectangle, the major difference is I'm not going to be using the left side of that first thing at all, right? So right here, I wouldn't be using any of that. I would start with the right side. So the right side here, if I look at it, the right side uses that they call that the H1 right here. So I look at that rectangle to find that. I'm going to bring the right side up. So I'm not going to use the -4 at all. I'm going to start with the 0 and do f of 0. Right? And then I'm going to use that and use f of 4 for my second one. And then I'm going to use 8 for my f of 8, right? And then I'm going to use finally 12 for my f of 12. And in this case, that gives me what? 144 minus a 36 plus a 4. So what is that? 112. So I would have 4, and I would be using f of 10. And I would find that area. So once again, you'd have your 16 and your 32. I think that was an 8. Hold on. 16 minus 12 is 4 plus 4 is 8. And then 176 and 4. Did I make an error?
I think
It's 12.
wait.
Oh, not 12, it's 10. No, that is 12. 12 in there gives me 144.
Just put a 10 with a 10 up there.
Oh, my bad. Sorry, F of 12. But I think I used it right. 144 minus 36 is 108 and 4 is 112. So when you add the area up here, how about I'm going to add these? That looks easier. 208 and then adding those 464. That right? 672. You can check my key, but that looks way different what I originally found, right? You know what makes me think? It makes me think that that parabola was looking more like this. And the left-handed approximations were way underestimating, whatever. And then the right-hand ones are way over approximating to get that much difference.
That looks like almost double too.
Sorry? It almost doubled in value.
Yeah, I mean,
But you'd have to check the key to see if I made an error. I'm sorry, I'm just kind of trying to get you some practice. All right, now, so what would that mean for midpoints? Okay, so here's midpoint. So I'm going to get rid of some of this to clean it all up. So midpoints, tell you what, let's just start. So let's just say I had, a curve up here. Again, I'm going from -4 to 12, and I'm still breaking it up into 4 parts, right? But this time, what am I doing? Right, that's 4048, but I'm finding the average, and I'm using that for my height. So what's the average of that? -2. That's the x value. Now, don't use -2 as your height. That's the x coordinate, right? So here, what is the area? I would say, okay, and again, it's really an integral, but I would say base, which is 4, times, and I'm going to be plugging in f of -2. So f of -2, which is right there in the middle. I plug it in to find that height. That gives me 4 plus 6 is 10, plus 4 is 14. And then there's my other base. This time, what am I going to use? Instead of -2, I'm going to use +2, which is in between 0 and 4. And I'm going to be plugging it in right here to find that height. So here's my f of 2, which gives me 4, and 4 is 8, minus 6 is 2. Right? And then I'm moving on to another base. And what's the in between 4 and 8? So I'm using 6. So I'm plugging in f of 6. That gives me a 36 minus an 18 plus a 4, which is 22. And I would think this one's going to be more accurate, way more accurate. It's probably going to be somewhere in between that 350 and 600. I'm guessing, whatever, 480 or I don't know. And then finally, between 8 and 12 is 10. So I'm plugging a f of 10 in there. And f of 10 in there gives me a 100 there and a -30 plus 4, which is a 74. And again, I don't know why I'm writing it on 1A. I'm technically doing midpoint. So this is C. So I technically should be putting it right there. I think you get that, right? So what is my total here? I get what? 56 plus 8 plus 88 plus 296. And maybe I'm not right on that. 64 plus 384, 448. All right, well, it is between there. But again, I don't know. I'd have to draw a picture of this card to see if that was logical. But I bet 448 is a lot more accurate.
If you average all of them.
Well, I wouldn't. I would go with midpoint or trapezoidal. Probably trapezoidal if I really want to. And I'd get more rectangles. Actually, if I wanted to, I would just literally use what you're going to learn as the fundamental theorem. Take the integral of that. You'll learn the fundamental theorem later. But it says take the integral, which is x cubed over 3 minus 3x squared over 2 plus 4x, right? Plus c. And then plug a 12 in, plug a -4 in, and subtract the 2. That's the actual area. That's using the integral. That's the fundamental theorem of calculus. And you know that, you just might not have known the name of it. But that's called the first fundamental theorem of calculus. There's two. All right. So that's what I'd really do. But I didn't have a formula for my backyard oval or whatever. So I just used an approximation. But I did a bunch of rectangles.
Yeah, how did you do it without like?
I measured the length of it. So let's just say my backyard looks something like this. Okay. So I basically measured the length right here, and I'm going to make up a number. Say that the length was 100 feet. So I said, okay, I just maybe use roughly 99. So every 1 yard, basically every yard, I calculated the length from there to there across. And I did a trapezoidal. I did basically height 1 times 3, height 2, height 3 times 3, height 3, height 4 times 3. And I did a little trapezoid. I measured those heights and did that. And I mean, I was money. I'm not kidding. I think it was shockingly good. And I remember laying aside going, I'm going to run out. I'm going to run out. Nope. Perfective. So, and people actually will use this. Like there's a problem I'll talk to you about stocking a fish pond. And it used to be really brutal. I kind of watered it down a little bit, but or made it a little bit more applicable and less real world, just more mathy. But you really could, by just looking at average depth, you can find the area of a lake that way. I mean, how else are you going to find an area of a lake? I mean, you could take a drone and take a snapshot and take that and measure it and get something to scale and maybe use Heron's formula. No, it's not Heron's formula. Do you remember that surveyor's formula in geometry, where if you have a bunch of data points, I don't know if you remember this, you can put all the points like this and then multiply the diagonals there times a half, and then multiply the diagonals, whatever there, and you can subtract them and find the area in between points. A lot of times people will do that, but if you don't have a drone, you literally can do this kind of stuff. I can measure lengths. That's what I did anyway. Worked for me. All right, last one, trapezoids. So again, trapezoidal, you're actually going to use every height, right? From the left to the right, not going to use any of the middles. So let's just say again, here's my curve. Here's your -4. Here's your, what are we going to 12? And I want 4 trapezoids. So that's at 0, at 4, and at 8. So how do you find a trapezoid? This would be D, trapezoid. So I'm going to go, all right, I need 1/2 times the base times the what? Sum of the heights. So for the first one, what 2 heights do I want? F of -4 and F of 0. So I'm going to have F of -4 there and F of 0 there. And what did we find for F of -4? Remind me. We've already done it. 32. And what did we, and then we found F of 0 was 4. Now, the great thing about the trapezoid is so that gives me this one. What's the next trapezoid? Still 1/2. If the base is unchanged, which it isn't in this problem, still 4. And I can borrow the F of 0 that I just wrote down. You're going to use it again, aren't you? Because in the next one, it uses F of 0 as the left part. So I'm going to copy that F of 0 back in there, which is 4. And now I'm going to find F of 4. And what was F of 4, remind me? 8. I'll put my 8 in there. And then for the next trapezoid, good, actually, it's the trapezoid. I'm going to reuse F of 4 and pair it up with F of 8. So I can reuse that 8 that I found from F of 4. And what was F of 8? 44. And then for my last one, 1/2 times base, I'm going to reuse my F of 8 and pair it up with my F of 12. And F of 8 was 44. And what did we say F of 12 was? Is it 108? No. 112. And yeah, the math's going to be a little brutal on this, but what could you do? Let me just show you a shortcut. And this is the formula they have you memorize. What can I factor out of all of this? A 1/2 and a 4. What is a 1/2 and a 4? 2. So here we go. I'm going to factor 2 out, and that gets rid of all of that. Now, what do I have left? all of these added together. And really, what do I have added together? I have 132 and what? 2 4s, 2 8s, 2 44s, and 1 112. Now, I'm not saying you have to do that. It didn't save me any time, but what if I had 100 rectangles or 20 rectangles? It might be easier to do that. Like some people literally just memorize the formula, 1/2 times base, and then they go first f of A plus twice f of B plus twice f of C plus dot, 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 twice f of whatever y, and then 1 f of z. You kind of see what I'm doing? Because all of these in the middle, there's 2 of them, but the one at the far left and the one at the far right only get used once. But you don't have to do that because in AP, they rarely ask you for more than 5 trapezoids anyway. I think 6 is maybe the all-time most, and it's just not that big of a deal to know this. You could still go 36 times 2, right? 2 times 36. You could go 12 times 2. And then you could go, 52 times 2. And you could go, 156 times 2. And it's just not that big of a deal to go 72 and 24 and 104 and 312 and add this up. And by the way, if you have a calculator, the only thing you'll be graded on is this setup. Like they want to see from you. They want to see 1/2 base times that, 1/2 base times that, 1/2 base times that, 1/2 base times that. It's really all you need to show. And then your answer.
Then once you put like F of.
You can, if you want to. Again, if you've got the time and you're not one of those who's always worried about finishing, if you're not worried about the time, yeah, take a couple extra moments and write. You can write this formula out if you want. I'm just saying you don't have to know it. It's listed somewhere in your packet, but you don't have to because it's not that saving you that much time when you only have 4, 5, 6 trapezoids. It's saving you a lot of time when you have 20 trapezoids because you can go to your calculator and go 32 plus 2 times 4 plus 2 times 8 plus 2 times 44 plus 112, as opposed to going 32 plus 4 plus 4 plus 8 plus 8 plus 4. It just gets more tedious the other way, I think. But what do I know? And then add all this up, and that whatever you got there, that would be your area. Are y'all with me? Yes, no? So those are Riemann sums. And I want to show you one other thing. We got what? How much time left? 5 minutes. Okay, I want to show you this. So sometimes they give you a table. And when they give you a table, almost always, not in this case, but almost always, the bases are different. Now, we normally have an x-axis and a y-axis. But if I'm dealing with time and stuff like that, we have a time represents the x, and then speed, velocity, stuff like that represents the y. Now, right here, they gave you speed, which is like velocity, but it's positive. Now, let me ask you a question. What happened before when we did XVA, position, velocity, acceleration? What happens when I integrate a velocity? It goes back to position. But what we really get is a change in position. Okay? A change in position is not the same thing as distance. For instance, if I'm standing here and I run a mile that way and run a mile back, what is my change in my position? 0. That's my displacement. That's what an integral will find. Okay? Now, if I move in the same direction the whole way, then my change in my position and my distance are the same. Okay? But if I'm zigzagging back and forth, then my change in position could very well be different than my change, than my displacement. Okay, displacement means how much have I displaced myself. Well, right here, look, my speeds are all positive, and I'm always running in the same direction. It says something like that right here. So if I want to do this, if this is my time, check it out. That's like my x-axis. This is like my x-axis. My speed is like my y-axis, right? That's like my velocity. So this is kind of like x and kind of like y. So what is my base if I went from 0 to 1/4? On time, what was the base? 1/4. What's my base if I go from 1/4 to 1/2? Another 1/4. From 2/4 to 3/4. So all of these bases, oh, but 3/4 to 1. All of these bases end up being 1/4, don't they? Very unusual. Now, this thing says to do what? Estimate the distance using a Riemann trapezoidal sum. If these are y values, how do I find the area, right? Think about this as a function with data points. How do I find the area if these are my two y values? I go what? The area is 1/2 times the base, 1/4 times what? 12 and 11. I don't even have to plug it in because it gave me the actual heights, the actual y values. And then I go, all right, next one. Not plus or minus. The next one would be 1/2 times the next base, which is again 1/4, times what? What are its y values? 11 and 10. And again, I don't have to plug them in because I'm not giving you I don't have to plug in 0 and 1/4 because they've already been plugged in and you know the y values. And then you keep going 1/2 times the base times 10 plus 10. And you're going to keep doing this all the way through what? 1/2 times the base times 7 plus 0. And again, what happens if this is a speed function, like a velocity function? Remember, Riemann sums are essentially doing what? Approximating area. And area is like an integral. So you are essentially integrating velocity to get a change in your position, which is displacement, if it's all positive, which it is, and you add it all up. All right, hey, do the best you can on these homework problems from yesterday and today. Just look through them, see what you can do. Have good questions on Monday, and have a great weekend. See you guys.
Literally almost every